One application of electron configurations is the ability to predict the magnetic properties of materials. And as we'll see, these magnetic properties are closely related to electron spin. Ferromagnetism is probably the most widely known type of magnetism, and it is exhibited by metals such as iron, cobalt, nickel, and certain rare earth elements, as shown here. Ferromagnetism arises when the unpaired electron spins line up in parallel with each other in regions called domains, as we see here. Now, even though within each domain there is a strong magnetic field, the bulk of material tends to be unmagnetized because each of the individual domains tends to be randomly oriented, as we see here. So overall, the material has no net magnetic moment. However, when these materials are placed in the presence of a strong magnetic field, the electron spins line up within each domain. And so the material then becomes magnetic. Paramagnetism is another type of magnetism which occurs when a material has one or more unpaired electrons. This creates a material that is weakly attracted to a magnetic field. And the example we have here is the paramagnetism of liquid oxygen. So here what's been done is we've taken oxygen gas, cooled it down until it is condensed to the liquid state, and when you pour this liquid oxygen in between two magnets, it will be attracted to the magnets and be suspended in air, as we see here. Diamagnetism is another type of magnetic property that occurs when all the electrons are paired. Okay? And this results in a material that is very weakly repelled by a magnetic field. So in the example we have here, we have a frog which is mostly composed of water. And because water is diamagnetic, if you place this frog above a strong magnetic field, then it will be completely suspended in the air because the water in the frog is repelled by the magnetic field. In this example, we are asked to predict whether the following elements will be paramagnetic or diamagnetic. The strategy for this question is first to look up the element in the periodic table so that we can write down the electron configuration. Then we can write down the partial orbital diagram for the element, and this will allow us then to predict whether the element is paramagnetic or diamagnetic. First, we'll start with part A, which is titanium. So, looking at titanium in the periodic table, we see that titanium is atomic number 22 in the periodic table. And so, we can write the electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. However, at this point we should recognize that the s orbitals are actually higher in energy than the 3d orbitals, and so we can rearrange this as 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Again, as I said previously, the 4s orbitals are higher in energy than the 3d orbitals. We can also write the condensed electron configuration for this. And so here we recognize that these electrons are the core electrons and represent the noble gas configuration for argon. And then these electrons are the valence electrons. And we have 4 valence electrons as expected from the group number, which is 4. So the condensed electron configuration is argon, 3d2, 4s2, and once again we have 4 valence electrons. 2 of those valence electrons are in the 3d atomic orbitals, and 2 of those valence electrons are in the 4s atomic orbital. So, starting with the electron configuration for titanium, we can write the partial orbital diagram for titanium. So, as we mentioned, the 3d atomic orbitals are lower in energy than the 4s atomic orbitals, so we write the 3d atomic orbitals first, and then we write in the 2 electrons in the 3d atomic orbitals. 1, 2 electrons. Next, we write in the 2 electrons that are located in the 4s atomic orbitals. 1, 2 electrons. And so here again we have our 4 valence electrons, 2 of them in the 3d atomic orbitals, and 2 valence electrons in the 4s atomic orbital. And so we can see here that since we have 2 unpaired electrons, titanium is paramagnetic. Next we take a look at chromium. Looking at the periodic table, we see that chromium is atomic number 24 in the periodic table, and therefore should have 6 valence electrons. So writing the electron configuration for chromium, we see that we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. You'll notice that in this case, we've written the electron configuration as 4s1, 3d5, and this is because chromium is one of the exceptions for electron configurations. And the configuration where we have 5 electrons in a 3d atomic orbital and 1 electron in the 4s atomic orbital is more stable than when we have 2 electrons in the 4s atomic orbital and 4 electrons in the 3d atomic orbitals. Again, however, we'll notice that the 3d atomic orbitals are lower in energy than the 4s atomic orbitals, so we will rewrite this electron configuration to show the correct order of the energies. And so we have 3d5, 4s1. Here we recognize that this part of the electron configuration is the electron configuration for the nearest noble gas, and therefore it represents the core electrons. And so we can write a condensed electron configuration as argon 3d5, 4s1. And so here we have 6 valence electrons as predicted from the group number. 5 of those valence electrons are in the 3d atomic orbitals, and 1 of those valence electrons is in the 4s atomic orbital. So for chromium, starting with the electron configuration, we can now write the partial orbital diagram for chromium. And again, the 3d atomic orbitals are lower in energy than the 4s atomic orbitals, so we write those 3d atomic orbitals first. And since we have 5 valence electrons in the 3d atomic orbitals, we have 1, 2, 3, 4, 5 electrons in the 3d atomic orbital and 1 electron in the 4s atomic orbital. And here we notice that we have 6 unpaired electrons, and therefore chromium is paramagnetic. Next, we'll take a look at lead. Looking at the periodic table, lead is atomic number 82, and therefore it has 4 valence electrons, being in group 14. We can write the electron configuration for lead as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 5d10, 4f14, 6p2. And so that's our electron configuration for lead. Again, we see that the 5d electrons and the 4f electrons are lower in energy than the 6s electrons, and so we can rewrite that as xenon 4f10, 5d10, 6s2, 6p2. And in this case, this represents the core electrons, and we have 4 valence electrons as predicted from the group number. 2 of those valence electrons are in the 6s atomic orbital, and then 2 of those electrons are in the 6p atomic orbitals. So starting with the electron configuration for lead, we see that we have 4 valence electrons, and now we can write the partial orbital diagram for lead. Since the 6s atomic orbital is lower in energy than the 6p atomic orbitals, we write the 6s atomic orbital first. So here we have 6s and our 6p atomic orbitals. We have 2 electrons in the 6s atomic orbitals, 1, 2 electrons in the 6s atomic orbital, and then 2 electrons in the 2p atomic orbitals, 1, 2 electrons in our 6p atomic orbitals, and you can see we have 4 valence electrons, as we expect from the group number for lead. And here we see that we have 2 unpaired electrons, and so lead is therefore paramagnetic.